Time dilation. Imagine hopping on a spaceship and flying close to the speed of light. When you come back, your friends on Earth have aged decades, but you've only aged a few years. Sounds like sci-fi, but it's real physics. This is time dilation, one of Einstein's wildest predictions from his special theory of relativity. According to Einstein, time isn't absolute. It ticks differently depending on how fast you're moving. The faster you go, the slower time moves for you compared to someone at rest. It was controversial when first proposed, but now it's been proven again and again. Atomic clocks flown on planes have ticked slightly slower than identical ones on the ground. GPS satellites wouldn't even work correctly without correcting for time dilation, both from their speed and their position in Earth's gravity. What started as a strange mathematical consequence turned into a real-world phenomenon we depend on daily. Einstein redefined our understanding of time, not as a constant, but as something that stretches and shrinks depending on motion. It's not just about science fiction anymore. Time travel, at least into the future, is baked right into the laws of the universe. Bending of light by gravity. In 1915, Einstein made a bold claim. Gravity doesn't just pull on objects, it warps the very fabric of space and time. That means even light, which has no mass, would follow a curved path if it passed near something massive, like the sun. It sounded absurd at the time. How could something as intangible as gravity bend something as elusive as light? But 4 years later, during a total solar eclipse in 1919, astronomers got their chance to test it. They measured the position of stars near the edge of the sun and compared them to where the stars appeared when the sun wasn't in the sky. The result? The stars had shifted. Exactly as Einstein predicted, light had been bent by the sun's gravity. That moment turned Einstein into a global scientific icon overnight. Today, we see gravitational lensing all the time in space telescopes, galaxies and black holes warping light from objects behind them like cosmic magnifying glasses. This bending of light not only proved Einstein right, it also became one of the most powerful tools we have to study dark matter and the distant universe. Gravity doesn't just hold you down, it shapes how you see the cosmos. Mass-energy equivalence, E is equal mc squared. Probably the most famous equation in history, E equals mc squared, wasn't just a clever idea. It was a revolutionary insight. Mass and energy are two sides of the same coin. Einstein's formula tells us that a small amount of mass can be converted into a huge amount of energy. The c stands for the speed of light, and since that number is enormous, even a tiny mass multiplied by c2 results in an explosion of energy. This prediction was tested and tragically confirmed through the development of nuclear weapons in the 1940s. A fraction of a gram of uranium or plutonium released the destructive force of entire cities. But the equation isn't just about bombs. It also explains how stars shine. Inside the sun, hydrogen atoms fuse into helium, and in that process, a bit of mass is lost, but not gone. It's transformed into light and heat, powering our planet. E is equal mc squared is the reason nuclear reactors work, why stars glow, and why the universe is anything but static. Einstein took something abstract, an equation, and revealed one of the deepest truths of nature. Mass and energy are interchangeable. That's not just math. That's the foundation of everything we see and feel. Gravitational time dilation. Einstein didn't stop at speed changing time. He said gravity could do it too. According to his general theory of relativity, time moves slower in stronger gravitational fields. That means if you live at sea level, time ticks slightly slower for you than it does for someone living on a mountaintop. It's not just theory, it's measurable. Scientists have placed synchronized atomic clocks at different altitudes and found that the one closer to Earth's center runs just a little slower. Why? Because gravity bends space-time, and in regions of strong curvature, clocks tick more slowly. It's a strange, invisible effect, but it has real consequences. GPS satellites orbit far above Earth and feel less gravitational pull, so their clocks run slightly faster than those on the ground. If we didn't correct for this time distortion, your phone's location could be off by miles. Gravitational time dilation also becomes extreme near black holes, where gravity is so intense that time nearly stops. Einstein predicted all this over a century ago, without any satellites, atomic clocks, or space stations. Today, we live in a world that proves him right every single second, literally. Time isn't a constant. Gravity decides how fast it flows. Gravitational waves. Imagine two black holes colliding. Not just an explosion of matter, but a ripple through the fabric of space-time itself. That ripple is what Einstein called a gravitational wave, and he predicted its existence all the way back in 1916. But for decades, scientists had no way to detect something so subtle. It's like trying to hear a pin drop from across the galaxy. Fast forward to 2015, exactly 100 years after general relativity, and LIGO, Laser Interferometer Gravitational Wave Observatory, detected gravitational waves for the first time. It wasn't just a triumph of engineering, it was a direct confirmation of one of Einstein's most abstract ideas. Since then, we've detected several more events, mostly black hole or neutron star mergers, and each detection opens a brand new window into the universe. Gravitational waves carry information no telescope can see. They tell us how space itself is flexing and bending. Einstein's prediction, once considered unprovable, is now a routine part of astronomy. And the more we listen, the more secrets of the cosmos we'll uncover. From a whisper in space-time to a scientific revolution, Einstein was, once again, decades ahead of everyone else. The cosmological constant and dark energy. Back when Einstein was crafting his equations of general relativity, he faced a problem. The math said the universe should be expanding or contracting, but the accepted belief at the time was that the cosmos was static. So he introduced a fix, a fudge factor he called the cosmological constant, to cancel out the expansion and hold everything in place. Later, when Edwin Hubble discovered that the universe was expanding, Einstein reportedly called the constant his biggest blunder. But here's the twist. It wasn't a blunder at all. In the late 1990s, astronomers found that the universe isn't just expanding, it's accelerating. And to explain that, scientists reintroduced Einstein's cosmological constant, now interpreted as the energy of empty space itself, what we call dark energy. So, in a strange full-circle moment, Einstein's discarded idea became crucial to modern cosmology. Today, we think about 70% of the universe is made up of this mysterious force. Einstein didn't know what dark energy was, but his equations left the door open for it. Even when he doubted himself, the universe was still playing by his rules. Redshift and the expanding universe. When light travels through space, it can be stretched, just like sound drops in pitch when a siren moves away. This stretching of light is called redshift, and Einstein's equations hinted that it should happen in a dynamic, expanding universe. At the time, the idea was radical, but soon after, Edwin Hubble observed distant galaxies moving away from us, and the light from those galaxies was indeed redshifted. The farther away the galaxy, the faster it seemed to be receding. This wasn't just motion, it was the very fabric of space expanding, just as Einstein's equations allowed. Redshift became one of the most important confirmations of an evolving universe. Without Einstein's groundwork, Hubble's discovery might have seemed like a cosmic accident. Instead, it launched modern cosmology. Today, we use redshift to measure distances, to estimate the age of the universe, and to understand the Big Bang itself. It's like a cosmic speedometer built into the light of the stars, and Einstein helped write the manual, The Precession of Mercury's Orbit. For centuries, astronomers noticed something strange about Mercury. Its orbit didn't behave exactly as Newton's laws predicted. It was off by just a tiny bit, like a wobble in the planet's path. No one could explain it. Some even guessed there was an undiscovered planet tugging on Mercury. But in 1915, Einstein's general relativity gave a stunning answer. His equations perfectly accounted for the anomaly. The extreme curvature of space-time near the Sun altered Mercury's motion just enough to match observations. This wasn't just a fix, it was the first direct success of general relativity. A tiny discrepancy in a planet's orbit became the proof that space and time bend under gravity. It was like discovering that the rules of the universe needed a rewrite, and Einstein had already written the new script. Today, we use these same corrections when tracking spacecraft near the Sun or calculating orbital mechanics. What was once a mystery is now a textbook example of Einstein's genius in action.